Hello again, I'm your guide, Engineer Mikko de Torres, and in this video, we're going to explore an essential aspect of mechanical manipulators, the number of degrees of freedom. Degrees of freedom, or DOF, is a fundamental concept in robotics, encapsulating the essence of a system's flexibility. It refers to the smallest set of independent parameters, variables, or coordinates required to fully characterize a mechanical manipulator. In simple terms, degrees of freedom gives us insight into how freely a robot can move and interact with its surroundings. Let's delve deeper into this crucial aspect. Let's take a moment to explore the concept of degrees of freedom using a relatable analogy. Imagine you're observing a mysterious 3D object suspended in space. Its exact identity, position, and orientation remain unknown. Now, to comprehensively describe this enigmatic object, we employ the notion of degrees of freedom. So first, it is called the spatial description. We will begin by this object as having an associated 2 degrees two-dimensional, or rather, Cartesian coordinate system. Adjacent to one of the object's surfaces, depending on where you're observing it from. So, this is where we are observing this surface. Okay. Then next is the variables for precision. Instead of relying on vague terms like upward, forward, downward, left, or right, we opt for precision. We introduce two key variables, x and y. Think of x as representing the object's position and orientation horizontally, while y signifies its vertical description. Then, in this context, x and y become the degrees of freedom, or the dig of f of our object. This means that with these two variables, we can fully characterize and define the object's spatial properties. By assigning values to x and y, example, if x is equals 5 units or y is equals to 10 units, it will describe the position of our object. Whatever our object is, we effectively unlock the ability to convey the object's position and orientation within the 2D plane. In essence, our object possesses 2 degrees of freedom. So, x and y is the 2 degrees of freedom. So, this is 1 degree of freedom. This is another 1 degree of freedom. So, if we add this is 2 degrees of freedom. Okay? This will allow us to precisely comprehend its spatial arrangement, just as this analogy simplifies the description of the object. The concept of degrees of freedom enables us to understand the level of movement and maneuverability a mechanical manipulator has in the world of robotics. Understanding the concept of degrees of freedom, or DOF, is essential in grasping the flexibility and movement potential of robotic system. Imagine you're looking at various objects in space. Each object has a certain level of freedom to move and orient itself. We quantify this freedom using the term degrees of freedom. When we talk about degrees of freedom, we're essentially counting the minimum number of independent parameters needed to fully describe the movement and orientation of an object. Let's break down with a few examples. So the first example is a point. According here, a point in a 2D space can move along two directions, horizontally and vertically, giving it 2 degrees of freedom. So just like our 3D object, let's represent a point in space besides a 2D Cartesian coordinate system. So this is a point. Let's name it point P. Okay. So we can describe this by assigning the variable x for the horizontal position and y for the vertical position. So these x and y are the degrees of freedom. In total, a point has 2 degrees of freedom. In a 3D space, with the addition of depth z, it has 3 degrees of freedom. So if we have a point here, and this is x, this is y, this is z, because this is the depth, and this is y. The degrees of freedom now is 3. Okay, so direction along horizontal for x, direction along vertical or vertically, this is z, then y for forward or backward. Okay, so we can describe the point at 3D space like this. Next, a rigid body like a solid object in 3D space has even more complexity. It can move in 3 translational directions, x, y, z, and rotate around 3 rotational axes, the roll, pitch, yaw, resulting in 6 degrees of freedom. So, example of a solid object in actual scenario is a flying plane. Okay, so a flying plane is a rigid body. Okay, a flying plane is a rigid body. It can move forward, back, then backward, left or right, upward, and downward. So we described it as x, z, and y. Okay, those movements. Our plane can also rotate along x, which is also called roll. It can also rotate along the axis of y, that is also called pitch. And it can also rotate along the axis of z, which is called yaw. So we have 3 degrees of freedom for the position. Then we have 3 degrees of freedom from orientations. So a total of 6 degrees of freedom. Okay? Now let's look at manipulators. A planar manipulator, which moves and operates within a plane, has 3 degrees of freedom. Think of a robotic arm on a flat surface. This is an example of a planar manipulator. It has 2 degrees of freedom. Unlike the unlike the rigid body, we count it has its own computations of degrees of freedom. Okay, so in this example, we have 2 degrees of freedom, but the ideal number of degrees of freedom of a planar manipulator is 3. On the other hand, a spatial manipulator operates in full 3D space, offering 6 degrees of freedom. This is the kind of freedom you'd find in many industrial robots capable of complex movements in all directions. This is an example of a spatial manipulator, and it has 6 degrees of freedom, an ideal spatial manipulator. Remember, these are ideal degrees of freedom counts, and in reality, mechanical constraints and limitations can influence the actual movement. Understanding degrees of freedom helps us design and analyze robotic systems effectively, ensuring they can perform the task we need them to. As we dive deeper into the world of manipulators, let's explore the different types based on their degrees of freedom, or DOF. Number 1 is an under-actuated manipulator. This type of manipulator offers fewer degrees of freedom than the maximum possible for its category. It can fall in two categories: a spatial manipulator with less than 6 degrees of freedom, or a planar manipulator with less than 3 degrees of freedom. Next is the ideal manipulator. An ideal manipulator has the maximum possible degrees of freedom for its category, offering a balance between flexibility and control. It can be a spatial manipulator with exactly 6 degrees of freedom, or a planar manipulator with exactly 3 degrees of freedom. Lastly is the redundant manipulator. A redundant manipulator provides more degrees of freedom than the maximum required for its task. Similar to the under-actuated manipulator, it can be of two types: a spatial manipulator with more than 6 degrees of freedom, or a planar manipulator with more than 3 degrees of freedom. In the world of robotics, the concept of degrees of freedom is closely linked to the idea of mobility. Let's break it down. Degrees of freedom represents the number of independent parameters needed to describe a manipulator's motion completely. It's a measure of its flexibility and capability to move in various ways. When a manipulator's degrees of freedom exceeds the ideal number for its type, it gains an extra dimension of movement. This surplus of motion beyond what's necessary for the task at hand is called mobility. For instance, if a special manipulator has degrees of freedom matching its ideal configuration, it's fully controllable and possesses no mobility beyond what's required. However, if the same spatial manipulator has more than 6 degrees of freedom, becoming a redundant manipulator, it gains mobility. This extra mobility can be harnessed for versatility, adaptability, and overcoming obstacles in complex scenarios. Remember, degrees of freedom and mobility play a crucial role in determining a manipulator's capabilities and applications. So next time you analyze a manipulator's design, consider the balance between degrees of freedom, ideal configuration, and potential mobility to optimize its performance. Now, let's dive into the mathematical side of things to calculate the degrees of freedom of a spatial manipulator. Grublers' criterion provides us with a structured approach. Imagine you have a spatial manipulator with n rigid moving links and m joints. Each joint I contributes to the manipulator's connectivity, denoted as Ci. This means the joint brings a certain number of constraints to the system. The number of constraints put by ith joint is given by 6 minus Ci, where Ci represents the connectivity of that joint. Adding up the constraints from all joints, you'll get the total number of constraints, or the summation of m from I equals to 1, 6 minus Ci, imposed on the system. Now here comes the key formula. The mobility or the degrees of freedom of the manipulator is calculated as 6n minus summation of m from I equals to 1, 6 minus Ci. This mathematical expression captures the manipulator's flexibility, telling us how many independent parameters are required to fully describe its motion. So if you're ever faced with determining the degrees of freedom of spatial manipulator, turn to Grublers criterion for an accurate and structured calculation. Now let's turn our attention to planar manipulators and understand how Grublers criterion helps us calculate their degrees of freedom. Imagine you have a planar manipulator with n rigid moving links and m joints. Just like before, each joint I contributes to the manipulator's connectivity, denoted as Ci. The number of constraints introduced by the ith joint in a planar manipulator is given by 3 minus Ci, where Ci represents the connectivity of that joint. By summing up the constraints from all joints, you get the total number of constraints imposed on the planar manipulator, or the summation of m from I equals to 1, 3 minus Ci. Here's the crucial formula. The mobility or the degrees of freedom of the planar manipulator is determined by subtracting the sum of constraints from 3n, the total number of dependent parameters in a 2D plane, or m is equals to 3n minus the summation of m from I equals to 1, 3 minus Ci. This formula serves as your guide to calculating the degrees of freedom of a planar manipulator using Grublers criterion. Whether dealing with spatial or planar manipulators, Grublers criterion provides us with a powerful mathematical tool to understand their flexibility and motion characteristics. Now that we've explored Grublers criterion for planar manipulators, you're equipped with a valuable tool to assess their degrees of freedoms. Stay tuned for our next video where we'll dive deeper into the process of solving for the degrees of freedom of mechanical manipulators. We'll guide you step by step through the calculations, helping you unlock a deeper understanding of how these remarkable machines move and function.